All right, what's up, people? I was going back through my videos because I wanted to watch something I did previous, and I can't seem to find those anywhere. And I never, no matter how embarrassing, I never delete any video that I make. So I figured, who the fuck? Who could have deleted that? Why does it matter? It doesn't matter. So I want to get back into something. So this video is not by me, of course, but we're just going to watch it because I figured I'd let a professional explain it.
And integers, numbers like 1, 2, 3, 4, and rational numbers, numbers like 3/5 or 5/7. And we said that these two infinite sets actually have the same size. And what we meant by that, what we meant by saying that infinite sets have the same size, is to say that there was some function from the integers to the rational numbers where every rational number got hit exactly once. And that this notion of a bijective function is what we meant by saying that these two different infinite sets have the same size. So now the question is,
Okay.
what about comparing something like the integers and the real numbers, where the real numbers are those that have things like pi and e and √2 in them? And what we're going to find out in this video is that in fact, those two different infinite sets, the integers and the real numbers, do not have the same size. And the argument we're going to be using is one that is due to Cantor, and it is a very famous diagonalization argument, and I'm going to show it in this particular video. The idea is this. Let's not try to compare to all real numbers. Let's just look at the real numbers that are between 0 and 1. And if it was the case that the integers and the real numbers had the same size, then we could find some function. We could line up the integers and the rationals, and we could pair them in this bijective way. So what I'm going to do is I'm going to try to list all of the different real numbers. Let's just make an infinite list. There'll be a first, a second, a third, and a fourth, lined up with the first integer, the second integer, the third integer, and the fourth integer. Now, I'm going to sort of make up which of these real numbers I want to go first and second. They could be anything. How about the first one could be 0.1? That's a real number in between 0 and 1. I'm actually going to go and write it in terms of its decimal expansion after the 0 point. So this looks like a 1 first, and then all the rest 0. 0.1000. Okay, how about for the next one, I'll do 0.333333, a decimal expansion for a third. It's another real number. Then I can do 0.1415926535897932, which is the first bit of the decimal expansion for pi minus 3. It's just kind of fun. I'm just putting some random ones in there. How about 0.99999, so on. This is a decimal expansion for the number 1. And then I'll fill up with 1 7s, 2 7s, 3 7s, and 4 7s, which have some cool patterns. You can see how that works. But the point is this. I've just chosen these at random. You can choose whatever ones you wish, and any other real number that you might imagine we're going to suppose could occur on this list. Now, what I want to argue is that no matter how you did it, no matter what choices I made or what choices you made for how we tried to line up the real numbers and the integers, no matter how we did this, that we could not get all of the real numbers. So now I want to draw your attention to these so-called diagonal entries. It's looking here at this first digit, the 1/10 spot, in the first particular row, the first real number we've identified, and then
Pay attention to this part. It's very important because what's going to be assumed here is a square. Because you have to have 1 in every column and 1 in every row. It's assuming a square, okay? So we'll let it go.
it's going to go down and it's going to go and look at the second digit in the second real number, the third digit in the third real number, the fourth digit in the fourth real number, and so on. It's this diagonal that we have here. What I'm going to do is I'm going to make a new real number that tweaks along this diagonal. So the 1 that we have here, I'm going to go and change that 1 and make it a 2. Then I look at the 3 that we have, that's in the second row in the second location, and the 3, I'm going to add 1 to it and make it a 4. The 1, I'm going to go and add 1 to it.
The argument was originally made in binary, which makes it much easier. And my counter to this argument is going to be made in binary. So if it was a 1, it would be a 0. If it was 0, it would be a 1. Now, he's using, a decimal scheme, but it doesn't really matter what base number you use.
Make it a 2. The 9 I'm going to add 1, but instead of making it a 10, I'm going to cycle around and make it a 0. So the 9 is going to become a 0, the 5 is going to become a 6, the 4 is going to become a 5, the 4 is going to become a 5, and the 7 is going to become an 8.
And because it differs from one in every place, it differs from every number on the list. But go ahead and get to it.
And what we have here is a new real number. This real number is not on the list. It's different from the first one, it's different from the second, it's different from the third. So no matter how you went about choosing your list of real numbers, we can always
Hope you can still hear this.
new real number that's different from whatever listing you might have given. And so this tells us that it is not possible to find a function from the integers to the real numbers that has this property that every real number gets listed exactly one time in association with the integers. There's not a bijective function between them. And so what this says in truth is that the integers and the real numbers, that they have a different size, that you cannot align them in this way. Now, we have some terminology for this. When you have an infinite set and you can line it up with the integers, where there's a first, a second, a third, and so on, we're going to say they're countable because you can align them with the counting numbers, and there's a fancy math symbol called a.
Okay, I'm going to have to kill that because what I need to do is I need to explain to you where this entire math thing went wrong. Okay? Because it definitely goes wrong. It assumes something, it assumes facts, not in evidence. Okay, so what I want to do here is, and what I have here is all the binary, 4 digits in order. So 001, that's 1. 0010, that's 2, etc. Okay? So I'm going to use this same argument on these numbers here. And when I do that, you're going to find something peculiar because what I'm going to do is, because I'm assuming the square, right? I'm assuming the square. That's the problem. That's the problem right there. Because if I do that and I take this number here, this number here, this number here, this number here, then what do I get? Going down the diagonal, I get 1, 1, 0, 1, right? If I do that, just doing the diagonal argument like he did. Now see, 1101 shouldn't appear on the list, right? Uh-oh. Look out. I found it. I found it. It's right there. It's right here. It's right here. It's on the list. So here's the problem with this whole diagonal argument. It assumes the square. Now here's the problem. I'm working with finite numbers, right? This guy's working with an infinity, meaning Cantor. Cantor's the dumbass that came up with this stupid ass. Look, we've known for centuries that the concept of infinity is plagued with fucking contradictions, paradoxes, etc. The whole, like, look, they want to say 1-to-1. What does 1-to-1 correspondence mean? Well, like, look, I can do this, right? Watch this shit. I can say, I can go, 1, 2, 3, 4, 5, etc., right? And then I can say, well, what about the evens, right? So it's 2, 4, 6, 8, right? So 1-to-1 means like this, right? That's what that means. So the set of the, the whole numbers is equal to the set of the evens. Except what if I did this? Like, what if I did 2 goes to 2, and 4 goes to 4, etc., and then 6 goes to 6? How's that not 1-to-1? That's 1-to-1. It just depends on what the fuck you mean by 1-to-1. And so what I'm maintaining in my argument about this fucking shit and about this whole diagonal argument is retarded is that you can make things go whichever fucking way you want them to go. So the fact that, you can draw a square around what they call in the transfinite analysis aleph zero or aleph null, you can draw a square around that, but how do you know it's shaped like a square? How do you know it's shaped like a square? You don't. Mathematically, you have no idea what it's shaped like geometrically. But you need it to be a square, because if it's not a square, your diagonal argument does not work. I found your 1101. I found it. Just further down the tree. In a place where you said it couldn't exist because you created the categories. So yeah, diagonal argument fails. There are no species of infinity. Infinity is beyond your conception. And all these fucking super silly, and I wish I could have all my videos back about this, transfinite math retards. They want to start talking about, hyper compact cardinals can go lick a dick. Infinity is beyond your comprehension. You just found another paradox. So sorry, you don't get a Nobel Prize. You don't get a Fields Medal. You get a Darwin Award.